You're listening to Worth Electronics' What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics' What's Up podcast. Now, for a long time, Worth Electronic has been the go-to for capacitors, filters, shielding, connectors, the list goes on. And now it goes a bit further in the Americas with a new extensive lineup of wireless connectivity and sensors. And today we are talking specifically about the absolute pressure sensor, the WSEN PADS or WSEN pads from Worth Electronic. An altimeter is an instrument and it measures the altitude above a fixed level. A number of different types of altimeters exist and it all depends on measuring principle, including pressure altimeters, optical altimeters, and radar altimeters. The pressure altimeters, which measure the atmospheric pressure to infer the altitude, they are the most widely used device in altimetry, and typical applications include indoor navigation and floor detection, industrial drones, GNSS enhancement for outdoor navigation, and smartwatches and fitness trackers. With the development of MEMS technology, pressure sensors are getting smaller and they're becoming more affordable. MEMS-based pressure sensors have gained popularity in recent years for their altimeter functionality. Now, they're used in various industries for activities such as hiking, climbing, outdoor and indoor localization to enhance GNSS or location-based services, indoor navigation, etc. The absolute pressure sensor from Worth Electronic is a high-precision MEMS-based digital pressure sensor with an I2C digital interface to provide accurate atmospheric pressure data. In today's podcast, we'll discuss the altimeter functionality of the absolute pressure sensor from Worth Electronic and the built-in sensor features like filters, offset calibration, temperature compensation, and more to help customers to implement the altimeter functionality with high accuracy. Now, before we dive into the formulas, we first need to discuss some basics of atmospheric pressure and altitude variation. Now, atmospheric pressure is the pressure generated by the weight of the air surrounding the Earth. At low elevations, a square meter on the Earth's surface has greater weight above it than at higher altitudes. As elevation increases, there is less overlying atmospheric mass, so the atmospheric pressure decreases with increasing elevation, whereas atmospheric pressure increases with decreasing elevation. So measured from sea level, atmospheric pressure approximately changes at a rate of 0.125 millibar per meter. But remember, this is just an approximation. Since the air is a compressible medium, there is a nonlinear correlation between the atmospheric pressure and the altitude. In Figure 1 of this podcast, we see the Barometric Formula that provides a correlation between the atmospheric pressure and the altitude. This formula is the atmospheric pressure is equal to sea level times the collective 1 minus temperature lapse rate times altitude divided by temperature. The lapse rate is the rate at which the temperature varies with the atmosphere. In our formula, the temperature lapse rate is 0.0065 Kelvin per meter. The troposphere, up to 11,000 meters, has a linear temperature profile with the altitude. As an average, the International Civil Aviation Organization, or ICAO, defines an international standard atmosphere with a temperature lapse rate of 6.5 Kelvin per kilometer, giving us a good approximation of 0.0065 Kelvin per meter as our temperature lapse rate. The Earth's surface gravitational acceleration equals 9.81 meter per second squared. The molar mass of dry air is 0.02896 kilogram per mole. The universal gas constant is 8.31432 newtons times meter divided by Kelvin times mole. These parameters are constant. Considering mean sea level pressure and temperature, the formula can be simplified even further. In this case, we have to consider the mean sea level standard pressure, which is 101.325 kilopascal, and the sea level standard temperature is 288.15 Kelvin. Based on this equation, altitude-pressure relationship can be plotted as shown in our previously mentioned Figure 1 of this podcast. So the correlation between atmospheric pressure and altitude enables use of absolute pressure sensors as altimeters. A sensor that is calibrated for the whole range of altitude measurement and has capabilities to fix the offset errors can be effectively utilized as an altimeter. Practically, the altitude of a point can be determined by the method described in these following sections. Used method varies depending on the conditions and the available information. In Figure 2, we can see the altitude variation with atmospheric pressure. At a point X, whose geographical height or altitude is known, the existing pressure at this point can be determined. At a particular altitude, pressure is measured again and then applied to the equation. Height relative to the point X can then be determined with the formula altitude minus height. But this is when the reference altitude is known. When the reference altitude is not known, a few extra steps are taken. In order to determine the reference altitude, first, the atmospheric pressure at this point is measured. Reference altitude can be determined by using mean sea level pressure and temperature. Calculated altitude is the absolute height at the point of measurement relative to the mean sea level. After ascent or descent, altitude can be found by measuring the atmospheric pressure again from the equation. This way, the relative height can be found. However, special weather conditions are not considered here. Accuracy of the measurement depends on the weather conditions because the atmospheric pressure always changes with the weather. So if weather changes during the ascent or the descent, resulting relative altitude would be incorrect. In this case, it's recommended to constantly monitor the pressure at the reference point, also known as that determined reference altitude. So how is it that you can use Worth Electronic WSEN pads as an altimeter? Well, earlier we discussed the relationship between the atmospheric pressure and altitude in our equation. Atmospheric pressure is measured against the vacuum as a reference, and this same reference is used in the absolute pressure sensors, so they can also be used as altimeters. WSEN pads is a MEMS-based absolute pressure sensor that includes a sensing element, analog to digital converter, filters, and digital interface that actually sends the digital pressure data to the host controller through I2C interface. MEMS-based sensing element consists of piezo resistors on thin side diaphragm connected in a Wheatstone bridge configuration. Upon deflection, it measures the applied pressure relative to the vacuum or zero pressure sealed inside the cavity of MEMS die during production. Difference between the external pressure and the vacuum causes diaphragm to deflect inward. This mechanical stress changes the bridge resistance and produces voltage proportional to the applied pressure. The ASIC performs amplification, calibration, and digital conversion. The ASIC also performs temperature compensation for the measured pressure value through the on-chip temperature sensor. Finally, the digital pressure data can be read through I2C interface. Commercially available pressure altimeters have a range between -1,000 to 9,000 meters with a display resolution of tens of meters. Apart from the resolution, measurement accuracy is also an important factor. Lifetime of the battery depends on the current consumption and the update rate of the sensor. The absolute pressure measurement range of the WSEN pads is between 26 and 126 kilopascal. This corresponds to the altitude range from -1,877 meters below sea level up to 10,109 meters above sea level. The absolute accuracy of the sensor as per the datasheet is plus or minus 100 Pascal, which corresponds to approximately plus or minus 8 meters in altitude. The absolute accuracy is the output deviation from the ideal transfer function over the operating pressure range. The piezoresistive sensing element is also sensitive to temperature changes and causes offset errors during pressure measurement. Therefore, real-time temperature compensation of the measured pressure plays an important role in order to achieve high accuracy. WSEN pads performs the temperature compensation internally with the on-chip temperature sensor. Apart from this, absolute accuracy is affected by several offset errors, which include mechanical stresses such as soldering and mounting, or aging. That's why relative pressure accuracy is important during altitude measurements. Next, we'll provide more information on relative accuracy. So relative accuracy is defined as the accuracy after removing the offset errors. In the built-in offset calibration registers of the sensor, users can write the correction values to eliminate the offset errors by performing one-point calibration. The offset values can be calculated via a calibration device or through known atmospheric pressure at certain locations. In our example, the accuracy is improved due to relative pressure measurement and thus by minimizing the corresponding offset errors. Since the relative accuracy is not affected by the offset errors, it provides much higher altitude accuracy. By implementing the relative pressure measurement in the altitude determination, further improvement in the accuracy can be achieved. In the practical measurement, a constant temperature and reduced pressure range needs to be considered. So how can a user measure altitude with Worth Electronics WSEN pads? Well, as we explained earlier, altitude is the vertical elevation of an object above a surface. Usually, the altitude at a point is defined above the sea level. Mean sea level pressure is 101.325 kilopascal relative to the vacuum or zero pressure reference. As discussed previously, the atmospheric pressure changes with weather. This change will also affect the mean sea level pressure. Sea level is not constant throughout the surface of the Earth, and therefore the sea level pressure is also not the same everywhere. These factors cause errors and inaccuracies in the altitude measurement. Actual sea level pressure and temperature needs to be obtained while calculating the altitude, and this information is regularly published in local weather reports. Along with measuring altitude, the WSEN pads can also be used in indoor navigation. Typical RMS noise of 0.75 Pascal corresponds to approximately 6 to 8 centimeters in relative height. This is the minimum change in pressure or altitude that can be reliably measured. This enables the use of sensors in floor detection as well as mezzanine detection. Pressure and temperature at the initial point can be measured from the sensor. During the ascent or the descent, the change of pressure can be monitored to determine the current height. In these measurements, the accuracy depends on weather conditions and the barometric pressure at the initial or reference point. Changes in the barometric pressure during the ascent or descent should be considered during the height calculations. Optionally, a second absolute pressure sensor can be placed at the initial or reference position that helps to measure the real-time barometric pressure. In attached figure 3 in this podcast, the WSEN pads was used to measure the height of each floor of a 6-story building with a basement. The sensor was placed in an elevator that stopped on each floor. In our image, the height of each floor was calculated with help of the barometric formula. A constant reference temperature is assumed. As for a short period of time and relatively small altitude change, the temperature changes can be tossed out. WSEN pads has special features integrated, and it supports the altitude measurements. By using the Auto Ref P or Auto Zero feature alongside the noise reduction filter, we're able to get very accurate relative height measurements. It's also possible to use the calibration registers in order to remove the offset errors due to residual stress after the reflow solder. When the built-in auto zero feature is engaged, first instantaneous measurement of pressure is stored in the reference pressure registers. Output data registers show the relative pressure, which is the pressure difference between the stored reference pressure. Similarly, AutoRef-P function can also be used to determine the altitude. When the AutoRef-P feature is engaged, first measurement of pressure is stored in the reference pressure registers. Current temperature and atmospheric pressure can be read via output data registers. Current atmospheric pressure can be used to determine the relative height with respect to the point where the reference pressure was obtained. In summary, altitude can be accurately determined by measuring the atmospheric pressure. The weather changes constantly and could have a large effect on the end application or the whole system. A sensor with built-in functionalities and on-chip offset compensation helps in eliminating the inaccuracies caused by such changes. WSEN Pads has integrated calibration algorithms and data logging features. Multiple selectable data rates, user-defined interrupt, and noise-reducing filter settings of the sensor enables highly accurate pressure and altitude measurements. This application note provided a brief idea on how absolute pressure sensors can be used to measure the altitude above sea level, as well as relative height above a fixed point. This makes the WSEN PADS sensors perfect for floor detection, weather station, GNSS accuracy enhancement, and the list goes on about who can benefit from these features and functionality. Attached images are available in most podcast streaming networks. To view all images, visit www.we-online.com/podcast. For detailed information about the AutoRef-P Auto Zero function and how it can be implemented, please refer to the user manual of WSEN Pads. To download the complete application note discussed today, visit Worth Electronic online at www.we-online.com/appnotes. You're listening to Worth Electronics' What's Up radio podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics' What's Up podcast.